title is Taming Horses in Singing Voice Detection, but we will first just focus on singing voice detection and come back to the horses a bit later. So the task, very briefly, is we're given some audio recording, and we want to know at which time somebody is singing. And I would just play the beginning of this, and I would ask you to just raise your virtual hand whenever you hear someone singing. Oh wait, I still have to enable sharing my sound. So let's see if it works.
Outside, snow is falling in the dark streets.
Okay, people hear singing voice.
And I can't seem to get no rest.
So if you would have followed through all the excerpt, this is when you would have raised your hand and lowered it. And this is exactly what we would like our computer to predict. Let's just assume that this is useful. I want to motivate this here. And the general approach, or most approaches that do this, and there are a lot of approaches that have been developed for this, can be framed as some kind of machine that analyzes a short excerpt of the audio recording and produces a number between 0 and 1, telling how likely there is singing voice at this position, at the center of the excerpt. So like this. And then once you have this machine, you can slide it over all the input and you will get a prediction curve. And then you just threshold the prediction curve to give you the result that you want. Now, most of these, most approaches which have been existing when I started this, when I did my PhD, were based on some manual algorithm like this. And so they did a lot of feature engineering, trying to find features that correspond to singing voice. And this is not really an easy thing to do. I mean, for you, it was very easy to know when to raise and lower your hand, but it's not so easy for you to describe to me as a programmer how you did this. So I could just copy what you did. So what people started doing later was to replace parts of this hand design by machine learning. And what I did for my PhD thesis was to replace almost everything of this with a single convolution neural network with deep learning. And there are two things that are left there that are very common to all the algorithms, and I will quickly describe what that is. So this is some feature engineering that we kept. So remember the recording that I showed you in the beginning. This is not actually all the data. If we zoom into this a little bit more, we see that there are a lot of data points. For this, it's 20,000 data points per second, and they vary a lot over time, and it's quite hard to make sense of this. You need to analyze quite a long excerpt of this to be able to figure out anything, and it's hard to find features that generalize well in this domain. So the first step that I kept from the hand-designed algorithm is to compute a spectrogram. This is what you see on the top here. So now we have the time going from left to right, the frequency from bottom to top. And so this is basically an image, and each pixel, it tells you how much energy is at that time point and that frequency. And you see now you have much more consistency over time, which makes it much easier than looking at the highly varying samples. And also you already get some kind of invariance. For example, if we would flip all the samples here, it would sound exactly the same to humans, although all the samples would change, but the spectrogram also looks the same then. So this totally makes sense. But now we're actually having more data than before because we're computing this with overlapping windows. So another step that I kept was to squash the frequencies a bit. And this is done in a way that is not linear, but that keeps the resolution at low frequencies almost intact and squashes higher frequencies a bit more. So we have this what we call MEL spectrogram, because it's based on the MEL scale, which is a scale that is trying to mimic pitch perception of humans. And there's another thing that I did that I didn't show now, which is changing the magnitude scale. Actually, if you would look at the original spectrogram, it would look like this. So it's a lot of very low values and a very few larger values. And this is not really good for machine learning, because we have a distribution that is highly skewed, and most algorithms expect something that is more Gaussian distributed, and we can easily get something that is more Gaussian distributed by taking the logarithm of each of these magnitudes. And this is what I have been showing you all the time, so you could see actually anything in there. Okay, so we have logarithmic magnitudes. This will be important near the end of my talk. So just putting this together, the design steps are now some machine that produces a MEL spectrogram for us. Okay, and on top we will put machine learning, and especially we will put an artificial neural network on top. And what we will be doing is, this is our task again. So we want to predict where there is someone singing, and we will consider a specific, more challenging task here. We will have training examples that are not labeled with any temporal accuracy. We only have one global label for each recording, which tells us, is there a singing voice in there or not? But it doesn't tell us where. And I will compare this with the baseline approach, where we actually have this full annotation, but fewer samples of those, only 100. And as I said, what we will put in between will be a machine consisting of this handcrafted feature design and then a deep neural network, which will read a short excerpt of the MEL spectrogram, here like 1.5 seconds, and it will output a single value between 0 and 1, telling us how likely there is singing voice at the center of the excerpt. And in between we have some convolutions, some max pooling. And we will then take the output of the network, apply some temporal smoothing and threshold. And I will have two variants of this network, one that takes the MEL spectrogram and one that takes the spectrogram without MEL scaling. This is because I will be doing some trick later on where I can extract the sound corresponding to the vocals. And for this, it's good to work in the original domain, not in the compressed one. And something peculiar about this architecture maybe is that I'm using small convolutions in the beginning and then one large convolution near the end. So these small convolutions allow us to learn features that are invariant over time and frequency. And near the end, I'm learning features that are still invariant in time, but take into account the full frequency range already. Now, this baseline that I'm comparing against has only 100 samples, and this would be a bit unfair. The other dataset has 10,000 examples. So I'm adding some data augmentation to enhance the variability in the training set. And I guess you may be familiar with this from computer vision. The catch was that for music, this had not been invented when I wanted to do this. So I first did some experiments on trying to figure out what kind of augmentations make sense for music. And you may imagine that rotating a spectrogram will not make much sense, for example. So what I tried was just adding some noise, some salt and pepper or Gaussian noise. I tried pitch shifting, which I implemented by just scaling the spectrogram because it was cheaper and worked well enough. I also like time stretching, same here, stretching the image a bit, changing the overall loudness, like making it quieter or louder, or applying some filters that would remove or quieten some of the frequency bands. Because all these transformations will not make humans change their mind on whether there's singing voice in there or not. And what I found was the best combination was to use pitch shifting, time stretching, and this filtering that I showed in the end. So this was what I used. And these are the results for our baseline, where I trained the network on 100 accurately annotated training examples on 3 different data sets. We will use this as a point of comparison now for the system that I'm training on the 10,000 weekly labeled examples. And now we will look at how I did this. So the situation here is now we only have global labels for our examples. And I started out very naively. I told, for negative examples, which are labeled as does not contain singing voice, I'm just propagating the label to all the positions in the input. And this is always correct, of course. If the example is labeled as contains voice, I don't know where the voice is, but I'm still just propagating the label to all the time points. This will be sometimes correct and sometimes not. And I'm just training a data classifier on this. And we get some results. They are not too bad, but they are also not really stellar. But it apparently learned something already. Now we can look at the predictions of this network for a training example. And we see that it doesn't actually reproduce the labels I gave for training, but it already has some dips at the correct positions. So maybe these predictions are actually better. They are closer to the actual ground truth than the training labels I started with. So maybe we can just use these as our new training labels. And this is what I did as the second step. I'm using the predictions of the first network as training labels, but only for the positive clips. For the negative clips, I can still set everything to 0 because I know this is correct. And these are the new results. They are considerably better, still not stellar, but better. And this all sounds a bit like Munchausen pulling himself out of a swamp on his own hair, but this is actually a common technique in multiple instance learning. So what can we do now? One might think we can just repeat this and get better and better results. But sadly, when I tried, it didn't converge to a good solution. It just kept predicting lower and lower outputs until it predicted there is no singing voice anywhere. So this was not going to help. But we can see that there is some interesting qualitative error the network makes here. It's always overshooting a little bit. So here the singing voice stops and it takes a little bit for the network until it also stops predicting singing voice. And the same on the other side, it predicts singing voice a bit too early. And this is a systematic error. And why is this? It's because of the way we trained the network now. If we look at an excerpt that has singing voice throughout, this is something that has always been presented as a positive training example, and it will give a positive prediction. Okay, if there's no singing voice, in the excerpt anywhere. This is something that has sometimes been presented as a positive example, sometimes as a negative example. So the network is less confident here, which is good, which is what we want. If there is some singing voice somewhere on the edge, this is something that has never been presented as a negative example, because this can only happen in clips that have vocals. So that's why the network predicts something positive here. Basically only learn to distinguish excerpts that contain singing voice from excerpts that do not contain singing voice. And I would like it to predict whether there's singing voice exactly at the center. So what can we do to fix this? We can ask the network if the central frame of the input was actually relevant for the prediction. And this is done by a technique called saliency mapping. Basically, we now invert the network and we compute the gradient of the prediction with respect to the input. This will show us which pixels have the strongest influence on the prediction. And we can draw this as a picture of the same shape as the input, and then sum this up over frequencies, and we get a new prediction curve, which is low at this example C. So this is what we will use as our new training labels now. Actually, I will squash them a bit using a tonnage, so they're more binary. And finally, when I train a network on this, it's getting results that are really close to training on accurately labeled data. Sometimes for one of the data sets, even surpassing it. And we can also look at the predictions. They are accurately following the training labels now, and they do not overshoot anymore. And something we can do on top is we can use the saliency maps as a extraction of singing voice from some input. And this is quite fun because we get this only from a data set with no information on where there is singing voice. It's just a data set that has been tagged as containing vocals or not vocals. And this extraction actually is competitive with some hand-designed singing voice extraction. Now up for the fun part. How does the net work? I will first show some example. This is the example we looked at in the beginning. And I will play this now and then switch between the different versions here. So this is the original input. This is the vocal track. So this is a data set where we know what the ground truth would be of just the vocals. And these are the extracted vocals from my network. And this is the hand-designed vocal extractor I talked about in the beginning.
Outside, snow is falling in the dark streets, and I can't seem to get no rest. I can't sleep.
This one has a lot of instrumentation still in there.
No, I can't barely breathe. So goodbye, triple arrow, my sentiment.
This is a little bit better. So I was quite happy with this. Now, there are some things that go completely wrong with this network, although it appears to be working fine. And I will quickly fix this, okay. And now we're getting to the horses. This is a horse, a particular horse that was taught by a mathematician teacher, a teacher of mathematics, a school teacher, to perform simple arithmetic tasks. So you could ask it, for example, Hans, that was the name of the horse, what is 3 plus 4? And then it would tap its hoof 7 times and get some sugar for this or whatever. So he trained it to do arithmetics, and he was very convinced that he was a good teacher, so he believed that the horse was actually capable of doing this, and he went around with that horse, and many people were astonished what it could do, and it could even do other things than just calculating. It could also, sometimes it did new dates, for example, so anything that it could answer by tapping its hoof, it could do. And of course, some people were a bit skeptical if this is really possible. And there was a psychologist who designed some experiments to figure out what was going on. And he found that the horse was not able to answer the question if the questioner didn't know the answer himself or herself. For example, you could do this by having two people tell the horse two numbers, whisper in one ear, whisper in the other ear. So none of them knew what the sum would be. And then the horse also didn't know. And with some more experimentation, he figured out that the horse was not actually doing math. Surprise, surprise. It was looking at the questioner, and the questioner would look at the hoof, and as soon as the correct number of taps was finished, he would involuntarily show some sign of relief or something. Ah, cool, it's correct. And the horse was very good at perceiving these involuntary cues, and yeah, tricked everyone into doing and to thinking it was doing math. And this is a bit similar with my model here. And yeah, Bob Sturm is a scientist also from the music information retrieval community, who has likened machine learning models to horses if they appear to solve a task, but are not actually solving it. And I found that this happens here as well. Oh, sorry, I have to. Oh, I cannot click the link because there's the menu. Now I can click it. So this is another example which seems to work well up to this point here. So there's this very long drawn node, and the prediction goes down completely. And also it's not extracted anymore. And interestingly, it's the same for the hand designed method. And it's completely gone. So what is going on there? There is clearly somebody singing, but the model is not detecting it. With some more experimentation, I figured out it's looking for some particular cue in the spectrogram, and I simulated this by drawing to a spectrogram. So what we hear here is a short piano excerpt, which sounds horrible because I resynthesized it from this Mel spectrogram without paying attention to the phases. I will play it for you once. And you hear there is no singing voice in there, and that's correct. The model also doesn't find any singing voice here. Now, if we add some, what's going on here? Some horizontal lines to this, and some other lines that look like this, and ask the network, it finds singing voice. And we can also listen back to what this sounds like. So what I found is that it's actually just looking for kind of sloped lines in the spectrogram to find singing voice, because this is something that that vocals can do, and that some other instruments can't. And this is what the network learned. So yeah, this is another demonstration. Whenever there is something like a wiggly line on top, it will predict singing voice. Now, how can we fix this? we could use data augmentation for this. This is what I tried. I'm just adding this as some augmentation to all the training examples, so the network learns to ignore it, and this works. It learns to ignore it, and my hope was that it would find a better feature than just looking for sloped lines, but it didn't. It just learned that on top of all that it learned before, it will not predict singing voice if there's this kind of wiggly line drawn on top. And there's another failure mode that I found, and this is even more curious. And I will start with the listening test again. So raise your hand whenever you hear singing voice in there. No singing voice, right? No singing voice at all. Let's ask the network. No singing voice. Well done. Now let's raise the volume a little bit. Raise your hand if you hear singing voice. So did anybody hear singing voice? No. Let's ask the network. Oh, there's singing voice. Interesting. We can also make it quieter, and then there's no singing voice. So what is going on here? It's in the data, actually. When we trained this network, we trained it only on files that contain singing voice somewhere. Now, this is a network that was trained on accurately labeled data. So it was trained on pop music, rock music, things like that. And all of these contain singing voice somewhere. And they have all been produced to make singing voice the most prominent instrument because it carries the lyrics. It has to be understood well. So singing voice in these data sets tends to have more volume than other instruments. And so the network learns that whenever something is loud, it must be singing voice, or it's a good indicator that there's singing voice. And we can try to fix this by adding some audio recordings that do not contain singing voice, that have not been produced in this way, like instrumental music. And then the correlation is gone. And we'll have another listening test for the new network. So raise your hand when you hear singing voice. No singing voice. Now let's ask the network. No singing voice. Now we can make it louder. Still no singing voice. We can also make it quieter. Oh, damn it. Let's try again with another one. Raise your hand if you hear singing voice. Network, there's singing voice. We can make it louder and it's gone. We can make it quieter and it's also gone. So what is going on here now? Let's look at the distribution again. We see there is no linear correlation between the label and the input magnitude anymore, but it's clearly still statistically dependent, because otherwise the two histograms should have the same shape, just maybe scaled differently. So there is some statistical dependence, and the model will just make use of it to get better predictions. So that's why it exhibits some weird dependency on the input magnitude now. What can we do against this? This is another way of visualizing this. If we evaluate the network on the original test set, it gets some performance. If we change the volume of all the test examples, the classification error gets worse. Okay, this is a simpler way to test this than doing the listening tests. Now we can again try to add data augmentation, like adding some loudness varied examples, but it doesn't really help anything. Why is that? if we look at this distribution again, adding some augmentation of the loudness will basically just spread out the two histograms a bit, but it will not get rid of the statistical dependency at all. Okay, so this is not helping. Then I tried some other methods like normalizing each excerpt before passing it to the network, or only feeding it difference over time. Or this is a method that basically normalizes the input with some exponential moving average over the past loudness or magnitude overall. And all of these work, but they give worse classification results. And then I invented a new method that is better than all the others. It's also completely loudness invariant, and I called it zero mean convolution. And the idea is, if you remember from the very beginning, we have spectrograms that have logarithmic magnitudes. So when we scale the sound in the input, the recording, to make it appear louder, this will turn into some shift in the logarithmic magnitudes. And what I did then was, for every filter kernel in the first convolutional layer, I constrained it so that the filter coefficients sum to 0. This will mean that any offset, any constant shift will disappear. And this way the network becomes insensitive to input level changes. So just to conclude everything, I showed some recipe to train in your network on examples that only have global labels, and it performed about as well as when training it on finely labeled examples. Although here now we had to use a lot more of the weakly labeled examples. So this is something that is useful if you already happen to have music with tags, as some industry players have, but it's not really useful if you have to label all the data first. Then I found that the network is likely detecting weakly lines. I couldn't really fix it well, and I found that the network is sensitive to the sound, which was not visible in the standard train test setting, and which I could avoid by customizing the model. So on a higher level, the conclusions would be, if there is any kind of bias in the data, the model will exploit it. In this case, it was, for example, the sound level. And finding these exploits will often require some custom interventions. And especially you should not rely on your test set to discover the biases, because if you have the same bias in your training and test data, you will never know that your model is biased. So try to leave the comfort zone of your test set if you want to apply your model on real data. And all the code is online on GitHub. All right, this was everything from my side. Thank you for your attention, and I'm happy to take any questions you may have.